Yeah. It's streaming now. So good morning everybody. We will take up the Green's function, and last time at KSOM I gave a sort of introduction to Green's function, and we'll make it more rigorous now and try to say what Green's function is, and maybe I'll repeat some of the things that I said there, but in a different way. Okay, right. So what is the problem? So we have to first take up the problem. Problem is, we have an nth order differential equation, something like Lx plus Q equal to 0, where L is sigma this is the n minus first derivative, and we assume Pi's and Q's and Q are continuous over some interval in. Could be the whole of the real line. So we take P belonging to, right. Now the problem is this. So the initial value problem is Lx plus Q equal to 0 with the condition since it's the inhomogeneous equation, the solution is not the trivial solution. Had Q been identically equal to 0, the solution would have been X identically equal to 0. Now you know that under the conditions that we have imposed on the coefficients, we know that the solution exists uniquely for this particular initial value problem. So the IVP has a unique solution. Now what we want to do is the following. Of course, we are interested in, given a particular Q, we are interested to find the corresponding solution. But now suppose you take all the continuous functions, the whole class of continuous functions on the interval AB, and for each one of them you want to find out the solution. So is there any way in which this particular solution can be described with a universal representation? Okay, I hope you get my point. The point is this. See that the initial value problem, actually what it does, okay, you take this expression Lx take the expression Lx. What does it give? For a Cn function, n times continuously differentiable function, Lx gives you CAB for every x belonging to n, that is n times continuously differentiable functions on A. So this works like a machine. Okay, so what you have is this. You have a machine here. This is the L operation. Now you have functions put in there, that is the input, and this is the output. So if you put a function x belonging to this class, then what you end up with will be an Lx, which is a continuous function. This is what you get. Now our problem is this: can you design an inverse machine so that given any q belonging to we get x determinant. Of course, we are, when we put this initial data also, then we are putting all these conditions also. Okay. Yeah. So what you need is, you fix this q. When you fix this, what is the, so you have to go back from here and get here. You have to reverse the machine and then get the corresponding, or define or design the inverse machine so that when you put q into it, you get the corresponding solution. Essentially, you solve the problem. Okay. So this is what we want to design. Okay. What would be the nature of this inverse machine? You look at our familiar, suppose x derivative is given by some qt or some gt. Then what do you get? You get x as integral plus a constant and so on. There is some kind of arbitrariness associated with it. Okay. So you get this. Maybe a constant also, because you whatever constant you add, you keep getting the same thing. Okay. So from G we are able to, through integration, we are able to, so say something like a to t. Yeah. We are able to get back the solution of the problem. So our machine consists of just feeding the corresponding function g here and getting it. So you see that when you have the machine consists of, the original machine consists of differentiation, then the inverse machine consists of integration. Or this is essentially, you transform this problem into solving an integral equation. Okay, or just computing it, and you find out the integral equation and do it. Now this is what we have at our hand is a more general problem where L is an nth order linear differential expression. We will see how we can try to get the solution of this problem. So for that we consider this problem itself. X derivative is equal to gt, and then this is something like this. Okay. So how do you rework this particular problem? Okay. Yeah. Now for that we make use of the following fact. Suppose you consider a function HST. HST is defined to be 0 for and equal to 1 for t. This is called the Heaviside unit function, as I said last time. Whose graph is of this form. It is okay, we are working on the interval AB. Then S is an arbitrary point on the interval AB. Then you take the function to be identically 0 up to this, and from then onwards it is, this is the function. This is identically 0 and 1 over. Okay. So this is HST. Now you know that H is not differentiable at St equal to S. Wait, I am talking about differentiability with respect to t. At t equal to S, it is not differentiable because it has a jump discontinuity. Elsewhere, H derivative is 0. So H derivative except at t equal to S. I have put S as a parameter because for each S we want to use this. Okay. Now what do we have? See, we take this integral A to B G derivative t. Okay. G derivative t. So this is equal to integral S to t and we assume that G vanishes b. I mean, this is just for convenience. Otherwise, it doesn't matter. You will get some number coming out. Okay. But this is equal to what? This is g uh, sorry, gt gb minus gt. And gb is of course a constant. Sorry, what is it? gb minus gs. So gb is a constant, and this, I mean, it doesn't matter. So when you differentiate it, this constant won't come into the picture at all. This we observe. Now we don't need this assumption, so we shall drop that. It's not necessary at all. Now just to do something which is not sensible, what I do is this. I write integral a to b had this been a nice function, okay, you can integrate by parts and you end up with what is called integral s to b with a minus sign. So what will you get? Provided everything is nice. I mean, I don't claim that this is differentiable everywhere. This is differentiable almost everywhere. So just one point where things go wrong. But certainly this makes sense. This integral makes sense. So we give a meaning to this integral by this. So take it as the definition. And if that is so, then this is equal to integral. What is that you have? You have, sorry, this is a to b. Plus some constant will become here. That doesn't matter. So this is equal to, so that constant we set as, I mean, here you have to possibly assume g b equal to 0. Let us keep this for the time being, but it doesn't come into the picture. So I am just giving a sort of feeling for the problem. So what you get would be integral t to b this is g derivative. G derivative of with a minus sign. This is going to be, yeah, this minus sign is there. Therefore, this is going to be GB. GB is a constant. So in this constant of integration that we do not bother, if GB equal to 0, then this is going to be 0. So you get GT in this way. Therefore, see, with the development of mathematics, I mean, initially this is the Green's function, these kind of things were not recognized. It was recognized that the Heaviside unit function, when differentiated, will give you the so-called Dirac which is a misnomer actually. And this function was considered as something, or at least physicists considered it as something which is identically 0 everywhere except at the point t equal to s, where it was considered 1. And this is the primary property that I have taken, namely that delta picks up the value of the function t. In fact, what they did was they looked at this function, the one I have defined, g t or delta t picks up the value f0. As you can see that this is and according to the physicists, they said that the function is identically 0 everywhere except at the point t equal to s, where the function takes the value infinity, etc., etc. All those nonsense was talked about, which mathematicians did not accept, and it's all a part of the history now. And mathematicians later discovered that this operation, which is symbolically written as an integral, this is only symbolic. Is essentially something like t s, sorry, t g, which will give you that means g is mapped to its value at the point t, if you keep t fixed. Okay, so this was the, so it's a functional, and you can easily see that tt is a linear function. On an appropriate function space. Okay, let us not go deep into that, and you will learn about this. This leads to what is called the theory of distributions. Those who are interested to know more about it, they can look up Rudin. Or Yoshida functional analysis. This gives books give you a good account of that. I am not going into the details of that. If we have occasion, we will go into the details of that. I know that I have been messing up a bit with the notation, etc. But things can be straightened out. There's no problem. But okay. So you see what I have defined here, what you get as solution is something like this. Yeah. So let me work out now the theory. So what you get as the Green's function for this problem is something like HST, and so that H prime ST or HST, so that you have this. So we take the solution as HST. Yes. And this, therefore, what you call y derivative of t is equal to integral, differentiate this, so you get h prime with respect to t of st gs ds, which we have seen is essentially g. Okay, so this becomes the defining function of the so-called inverse machine in this particular case. Okay, so what we are trying to do is to obtain something like this, and in the more modern explanation for what is going on is this. See, you see that this becomes what is called the delta function borrowing physicist notation or keeping to the conventional notation, this is equal to GT. So H this is the sort of identification that you have when you get this. There are physical interpretations of this, and in fact it is physicists who got this out. And as I was telling the other day, physicists have all advantages because they don't have to bother about the mathematical niceties. They work with intuition. They always work with intuition and not with the mathematical rigor or rules of the game. All these things do not matter for them. So they can differentiate wherever the function is. So they just discovered something very, very funny, because they defined the delta function as delta st was as a function of s was considered to be 0 everywhere except at s is equal to t. And at s is equal to t, they defined it as infinity, and by any stretch of imagination and the theories that mathematicians developed, this integral will have to be 0, cannot be gt. But the property of this particular object, what you call the delta function, is that it picks up the value of g at t. So just keep it in mind. You are going to encounter this in future somewhere, and you would know more about this. In fact, this is a sort of what you call Fields medal work. Eventually, the legitimatization of the Dirac delta function led to the theory of distributions, and it's a Fields Medal winning work by L. Schwartz, and this is called the theory of distributions. Okay, so let me come to that. So let me stop with that. Now we will go to the classical Green's function. Okay, so we have to define what the Green's function is all about. Our problem is this. Zero with now we define what is the Green's function. Let be a function defined over such that 1 and its first n derivative exists and satisfy Lx equal to, that is a homogeneous equation associated with that, Lx equal to 0, except, this is the important part, except at the single point so the function and its first derivatives are solutions of the equation Lx equal to 0, except at the point t equal to s, where you allow it to be whatever that comes out. Now we will put some restriction on that. The second condition that you give is that the function x derivative n minus 2 derivative exists and are continuous on the interval AB that means they are assumed to be continuous at S also. Further, and x n minus 1, the n minus first derivative of x is assumed to have a discontinuity in fact a discontinuity of the first kind, okay, at t equal to s given by x n minus 1 is n minus first derivative at these are the assumptions that we make. In fact, we shall see that this is redundant. If it exists, is called the Green's function. It's also sometimes called a weighting function. It's probably an old terminology, okay, but this is certainly this would have come from the physicists. Weighting function for L for Lx and is denoted by Kst. And this is also in the literature sometimes denoted by okay, let us see what exactly it means. It means the following. See, you have the interval now S is some point. Now what we assume is that you have the equation Lx equal to 0 with the initial data n minus 1. Okay, this is the homogeneous equation with these conditions. Now you know that the only solution, so it's a well-defined initial value problem, it has a unique solution, and the unique solution has to be x identically equal to 0. So x identically equal to 0 is the solution for the problem Lx equal to 0. But what we are going to do is the following. We take a point S lying between A and B. Now we take xt, we look at a solution with the following properties. The first thing that you demand is that Lx equal to 0 on this part. That means except at the point S. Okay? And what you assume is that the n minus first derivative of discontinuity, which is more specifically prescribed in this form. Okay? Let us see what you get. So you start with the problem on the interval A to S. With the initial data here. So what is going to be the solution? The solution is going to be identically. Now what we have is that, so this condition is automatically satisfied. Because the function is identically equal to 0, the n minus first derivative, when you approach the point from the side s minus 0, it is going to be 0. So that condition is automatically satisfied. What about this? So what we do is we solve the problem again on the interval. So we take Lx equal to 0 on the interval S to B. Set the following condition. So what you do is you see that the function is continuous everywhere. Not only it is continuous everywhere, but all the derivatives up to the order n minus 2 are continuous. Okay, therefore you have x derivative etc. up to n minus second derivative, picking up the value 0 at S. The continuity of x and its derivative up to the order n minus 2 sets x s equal to x derivative s equal to 0. And what about the n minus first derivative? N minus first derivative is not equal to 0. That is the condition. X n minus first derivative at S. So we are rigging the initial data at the point S. You see that because of these conditions, that these functions, these derivatives exist and are assumed to be continuous on AB, and therefore you see that the derivatives at S are automatically, because it's identically 0 function, the derivative at the point S the derivatives up to the order n minus 2 of x at the point s is 0. But because of this prescription, x n minus 1 s plus 0, that means when you approach from here, is equal to minus 1. So we take this as this one. Once again, it's an initial value problem. It's a new initial value problem on the interval s to b with a non-homogeneous initial data. On the interval a to s, it is a homogeneous initial data. Therefore, you get identically 0 solution. But here you get a non-homogeneous initial data because of the jump discontinuity that we have given for the n minus first derivative. Okay. So what do you expect? The solution is non-trivial. That means x is not equal to 0. Okay. So you have gotten, in fact, the n minus first derivative see the function defined as 0 here, and beyond that there is some function like this. Okay, it has a discontinuity, jump discontinuity. Okay, or sorry, I think I should, because the way in which we have defined it, something like this. So it is minus x of the n minus first derivative at s is taken to be okay. I don't know. It will be a non-trivial one because the n minus first derivative is going to be equal to minus 1. So something like this. Okay. So let us look at some examples. Then it will be clear what we are saying. So this function is as, and kst is equal to 0 for and this is equal to the function xt, which is not identically 0 on the interval s to, there is no form, no point, no ambiguity in writing even equal to here, because it is only the n minus first derivative which has a discontinuity, otherwise it is 0. Therefore the function is continuous. Not only the function is continuous, but the function and all its derivatives up to the order n minus 1 are, up to the order n minus 2 are continuous. Okay, therefore these conditions are satisfied. Where did I write that? So these conditions are satisfied. But there is a jump discontinuity, and this jump discontinuity is going to do the job. Okay, in defining our inverse machine, this jump discontinuity is going to be the factor, as we have worked with that simple example. Now let me come back to this, the problem. Want to integrate this on the interval zero. Okay. What will be the Green's function? Let us take the initial condition at x at 0 equal to 0. What is the Green's function for this problem? You know that this equation has a non-trivial solution as long as G is non-trivial. So what do you get? Let us set up the Green's function. So you take the interval 0 to 1, you take S, and on this portion the function is, so xt is identically equal to 0 on now you see that you are talking about the n minus first derivative, and n is in this case equal to 1. Therefore, you are talking about the 0th derivative. That means the function is going to have a discontinuity. So what is that? So we have to solve this problem. Dx by dt equal to 0 on the interval s to 1, with the condition that x at s is taken as minus 1. So let us solve this problem. If you solve this problem, you immediately see that if you look at the homogeneous equation dx by dt equal to 0, what are the fundamental set of solutions for this, or a linearly independent set of functions which satisfy this? You see that 1 and t form a linearly independent set of solutions for this problem. Okay, and we want to use this on the interval s to 1. So on s to 1, sorry, I think did I, no, so sorry, so in this case of course there is only one solution because it's a first order equation. Therefore 1 is the solution. Therefore in fact you see that in this case what you are asking for is, I think I made a mistake, I was confused with the problem. So you have x s xt defined as 0 for t less than s and equal to minus 1 . This is the function. The function itself has a discontinuity, and this is what is called your sort of minus h that you have. Okay, this is what you, in our earlier notation it is going to minus h. Okay, so if you allow s also to vary now on this interval, then you get HST defined as this is the Heaviside unit function, and our KST in this case is equal to minus . And you can easily verify that integral 0 to 1 solution of the problem x derivative t equal to g. So that I leave it you to verify. But maybe this is a too trivial to give you some insight into the problem. So let me do a more non-trivial case. So let me take L to be x second derivative. I was confusing some notation with this problem in my mind. It came into my mind. So this is our problem is this: Lx equal to 0 with the initial data or x0 equal to 0. X derivative 0. Now you take the interval 0 to 1. Take the point S. On this portion, we solve the problem equal to 0, subject to the condition that x0 equal to x derivative 0 equal to 0 for t belonging to 0 s. What is the solution? The corresponding solution is xt identically equal to 0, because that is the only solution that you have. Okay? So that is for this. Now for t belonging to s to t, the problem is to get the k, to solve Lx equal to 0 with the condition that x s equal to 0, x derivative of s equal to minus 1. Okay, that is what you have to solve. So that you can see the definition of the Green's function. If you put these functions together on the interval 0 to 1, you will get the Green's function. Let us compute this. Okay, when you compute this, this is what turns out to be. So what is xt? See, you are looking at this equation Lx equal to 0, which is x second derivative equal to 0. You know a fundamental set of solutions are 1 and t is a fundamental set of the solution space. Therefore, the function that we want to, so we want to solve this equation. Let us do that. So you need this to be solved, that is x second derivative equal to 0, subject to the condition that And you can easily see that this is a linear combination. So write xt as C1 plus C2t. Now use the conditions. X s equal to 0 gives what about x derivative of s? Minus 1. This is what we want. This implies if you take the derivative, so you are left with C2 equal to minus 1. Okay. So solve these two equations. To solve these two equations, so C1 now from this C1 is equal to because C2 equal to minus 1, you get C1 equal to S. Therefore, xt is equal to S plus C2 is minus 1 minus for S to 1. Therefore, what is your KST? This is equal to S minus T for, you can easily check that this satisfies all these conditions. Therefore, now later we shall see that this is, in fact, you can see that integral 0 to 1 which is a solution of this, you can verify. Come to that point later. Okay. I think maybe it is time for a break. So let me stop here and then we go to the rigorous discussion on this. So I will be returning by 11. Okay. Right. Do you have any questions? Hello?
Yes, sir.
You have any question?
No, sir.
Okay. Then we will meet at 11 o'clock, right?